In this video, we're going to design a 5-volt, 1 amp buck converter using Altium Designer. Hey everyone, welcome to another episode of Electronic Savvy. Today we're going to talk about how to design a 5-volt, 1 amp buck converter using Altium Designer. So in this video, we're going to take the same switcher IC that we simulated in the last video using LTSpice, and we're going to use Altium Designer to capture the schematic and do the layout. So here I have this LT8631, which again, in the previous video, I used the same switcher to simulate my circuit, basically all the passives, all the resistor values for feedback, input and output capacitor to simulate the performance of this buck converter. And then now we're going to take the same circuit that we simulated, and now we're going to design a real world PCB using Altium Designer. So for this application, we're assuming that the input voltage is a typical 12 volt. So again, for this design, we're assuming that this input power source has high impedance, or there is significant inductance really due to long wire and also the parasitics along the line. So we're going to use this bulk capacitance that basically provides a low impedance path for the high frequency energy to the ground. And also, as always, we're going to have some ceramic capacitors. We call them decoupling capacitors, that they must be placed close to this input pin. So the idea here is that we don't really have a capacitance that provides low impedance across all ranges of frequency. So what we need to do is we need to kind of mix up higher value capacitance with lower value capacitance in order to ensure that we have low impedance across different frequencies. So in this case, because this lower capacitance provides lower impedance for higher frequency, we want to place it as close as possible to the input pin, and then we're going to place the same ceramic capacitor but slightly larger capacitance right after that, because the important factor here is we need to place the smallest capacitance closest to the input pin, because it ensures that there will be minimum higher frequency noise at this pin. And also all that higher frequency energy will get decoupled to ground through this lower capacitance value. And then now, again, as we had it in the same simulation, I have this 2.2 microfarads connected to the internal regulator. Again, this is recommended by the data sheet. And then we have a bootstrap capacitor, a switch node, again, the same exact circuitry as the one that we just simulated in LTSpice. But hey, again, the idea here is that bootstrap capacitor provides that higher gate voltage than the source of the internal N-channel MOSFET. If you guys recall, we discussed that in the previous video, that in synchronous converters like this particular switcher, when there will be a high side switch and a low side switch, and when the high side switch is a N-channel MOSFET, we need to have a bootstrap capacitor in order to provide that extra bump in the gate voltage that allows that MOSFET to turn on and off fully. And then obviously, because this bootstrap capacitor connects to the main switch pin and carries a lot of high frequency noise, hence it will have high dV over dt component around this loop. So from the bootstrap capacitor to the switch node and back to the ground. So that's why I have this little blanket in here that highlights that this particular node, basically the bootstrap capacitor node as well as the switch node, will carry high dV over dt noise. So we need to make sure that this loop is as tight and as short as possible. And then again, this inductor pin, as we discussed it, feeds into the current sense, because this particular chip uses current mode regulation for the output voltage. So this pin has the same voltage as the output voltage, because there is only a resistor across the inductor, this IND pin and Vout pin, which is used to sense that current through this inductor. And here we have the Vout pin, which is again is the output of the buck converter. It's set to 5 volt using this feedback resistor. And as we discussed it, we need to have this 4.7 picofarads to ensure loop stability of the compensation network inside the chip, as well as two output capacitors. So the output capacitor in this configuration basically has two essential functions. Along with this inductor, it filters the square wave generated by this switcher to produce this output voltage, in this case 5 volts, and this determines the output ripple. And again, larger output capacitor generally correspond to lower ripple, but it does come up with a trade-off of inrush current and more required board space. Also, another function of this output capacitor is to store energy in order to satisfy transient loads and stabilize the switcher feedback loop. And again, depending on what value of output capacitor we select, we may have to adjust this particular capacitor because they do feed off the same voltage. But again, the details of what value it should be selected for this particular switcher is given in the data sheet. Based on the 5 volt output, it is recommended to have about like 33 microfarads, and then I also have like this 2.2 microfarad ceramic capacitor to filter out some of the higher frequency noise that may be present on this line. And going back to these values, we discussed it in the previous video. The larger an inductor, the lower the output current ripple. So in this case, I have this RT set to 8.66 kilo ohm, which correspond to having the high side and low side switch in the switcher switch at about 1 megahertz. So at switching at 1 megahertz allows me to select a smaller inductor relative to, for example, 440 kilohertz or something. That's why there is always that trade-off between how fast of a frequency are we switching this switcher and how much room do we have for the magnetics. Also, switching at higher frequency does correspond to higher switching losses because your switching frequency directly contributes to how much switching losses are there in the device, but it does help with the overall magnetic side of the circuit. Again, the TRSS pin is the soft start. I kept it the same value, the 2 nanofarad that we had in the simulations. And for PG and sync or mode pin, I have a 2-pin header just in case you wanted to hook it up to a microcontroller, or if you want to just measure if this pin is low or high, you can access it using this 2-pin header. And now, as one last thing, is I also put LED indicators just to give us an idea of whether or not this converter is fully functional. I have a LED indicator for the VN, and I have an LED indicator for the output voltage, which in this case is 5 volts. So in VN, I calculated based on the assumption of 12 volt input. Like this particular LED has a typical of 2 volt of forward voltage. And if we want to drive this at about 10 milliamp, we can just easily calculate the series resistor in order to limit the current through the LED so the LED don't burn out. Same equation applies here. It's just a simple Ohm's law where you calculate this resistance value based on the voltage drop across this resistor. So this is the schematic for this 5 volt 1 amp buck converter. Now we're gonna switch to the layout. So a couple points here. Every time you decide to design a switching regulator, it's important to pay attention to the stackup. I recommend using at least 4-layer PCB if you have some sort of a switching regulator. And the reason for that is it allows you to have a solid ground plane right underneath all the switching components to ensure that there will be the smallest current loop that goes from top to the layer underneath, which is ground, which hence will improve EMI and noise performance of your circuit. So look at the stack up of this buck converter, go to design, and then if we go to layer stack manager, this window pops up. What this is saying is in this stack up, I have a 4-layer PCB. All 4 layers are labeled as signal. The top layer is where I place all my components. In this case, it's all the input output capacitor, all the switchers, and all the passives around it. Right underneath it, I have ground. And underneath that, I can have a signal layer, and then the bottom is basically the same ground. Or you could have components if you want to. But in this case, because I wanted to make it as simplified as possible, it's best not to put any components on the bottom layer because it'll add cost to the fabrication of the PCB. Here I have the outer layers set to 2 ounce and inner layers set to 1 ounce. And the reason for that is I just wanted to ensure that this board can conduct 1 amp of current continuously with minimum thermal signature on this board. So again, going back to the same physics principles about thermals and resistivity, the larger the area of your conductor is, the better the thermal performance. And the reason for that is because you get less resistivity with larger. The most basic configuration for copper weight is 1 ounce on outer layers and half an ounce on mid layers. But again, because this is a relatively small board and I want to make sure that this board has no issues conducting 1 amp of current continuously to the load, I wanted to ensure that the board does not get hot. So that's why I switched to a heavier copper on outer layer and heavier copper in mid layer. And again, we have the core and the dielectric, the pre-peg dielectric between each layer in order to separate them. So this is a typical stack up for a 4-layer buck converter. So now that we took care of the stack up section, let's just talk about how things are placed. Again, on this board, I have C1, the input capacitor, very close to the input connector. And as we discussed it, C2 and C3 are the decoupling ceramic capacitors that are placed very close to the input pin in order to eliminate as much trace inductance effects as possible and source cleaner voltage to the IC. Again, that comes from the same idea that lower capacitance value yields lower impedance to higher frequency noise or higher frequency energies. That's why I have the smallest capacitor closest to the pin. And I have the PG power good and sync or mode right under here, which I just connected directly to this male header on top. And here we have an R2, which is, this guy is basically is just your RT that sets the 1 megahertz of switching frequency. Capacitor C1 is for setting the soft start time. And 5 volt is basically your output. Here I have the capacitor that's very close to the pin. This one is that capacitor 4.7 picofarad capacitor C6 that helps with the stability of the internals of the circuit. One thing that's important is to make sure that all the feedback network is very close to the IC to avoid any coupled noise from all the magnetics or anything else on the circuit. And I have this capacitor C9, which is that output ceramic capacitor that I have it again close to the IC in order to ensure that all the high frequency noise gets decoupled from the line. And I have a couple vias that are very adjacent to the 5 volt pad. And the reason for that is I want to make sure that there are enough vias to conduct all that 1 amp of output current to the load. As a rule of thumb, a typical via about this size, this one is about 12 mil of hole size and 20 mil of diameter. A typical via about this size can conduct about 200 milliamp of current each. So that's why I have at least 5 vias around here in order to ensure that all the current can easily go from the switcher all the way back to this output connector in here. And again, 5 volt is not really switching. It's not part of the hot loop in a sense. It's not part of the high frequency loop. So that's why I have this 5 volt switch from top layer into the 3rd layer, which I call it signal layer. And this signal layer basically takes that current from the 5 volts and it brings it all the way out of here to this output capacitor on top, again, to this output capacitor. And then this output capacitor does last set of filtering and it stores much of that energy and it supplies it out to the load with minimum noises. Again, in order to help with the thermals, I also dedicated another area in the bottom layer to the same exact 5 volt plane. As you can see, the 5 volt plane on the bottom layer is connected to the 3rd layer and connects to the first layer on top, which connects to the switcher. The reason for that, again, is to ensure that we have enough copper to conduct 1 amp of current, and we optimize thermals by increasing the available area for current to flow. Now, another point that I wanted to talk about is it's very important to keep all the magnetics. By magnetic, I mean input capacitors, output capacitors, as well as the bootstrap capacitor and the inductor all on the same layer as the switcher IC, because that's where all the higher frequency noise, that's where all the higher frequency energy is getting transmitted from input to output and back to the switcher. So it's very important to ensure that all your magnetics and all the main switching components are all on the same layer, and there is a ground layer right underneath that in order to ensure the smallest loop for the switching current to complete. So this capacitor C5 is the bootstrap capacitor that has to be placed very close to the IC, and the capacitor C4 is for the internal regulator, and here we have the inductor that's connected directly to the bootstrap capacitor switching node. You should not place any vias along this switch pad because, again, this is a high frequency switching and it must be placed on the same exact layer as the switcher, like in this case on top layer. And here is basically the DC pad of your inductor, which is used for the current sense. And again, this goes back to the same pin of the switcher to sense current. Again, because of the small spacing I have in here, I used a relatively thin trace, but this shouldn't be a problem because it's relatively short distance. And again, just to go through the stack up one more time, on top layer, I have all the main power planes. As you can see, the input is right here. We have all the passives as well as the feedback control circuitry and the magnetics all on top layer. And I have this huge polygon port that's on the top layer, and this layer is indeed the ground layer. So in most cases, when you deal with embedded systems or in switching power supplies, it's usually recommended to have ground ports all over your board that basically encapsulates all the other circuitry, and it ensures that there is always a lowest impedance path for this current to flow back to the ground. And again, that goes back to the same idea that I discussed, that on the top layer, we have this polygon port, and right underneath it has to be a solid ground port, which does not have any cutout, which ensures there will always be the absolutely shortest return path for the switching current. And again, on layer 3, I have this section for the 5 volt, just to help for the thermals. And on the bottom layer, again, same thing. I have the same 5 volt plane here, but everything else around it, it is connected to the ground net, similar to the signal layer, which connects to the ground net in this case as well. And one thing that it's always good to note is when it comes to multi-layer board, in this case, and you have multiple ground polygons that's poured all over your board on all 4 layers, one thing that you guys can do in order to further lower the impedance of your ground net is to via stitch your polygon ports. Via stitch is literally just what it sounds like. You basically stitching the grounds on each layer using vias. As you can see, these are the via stitches that are connecting the ground port on top layer to bottom layers. And the way that you can do that is you can go to Tools, and then you could scroll down to Via Stitching and Shielding and select Add Stitching to Net. Once you select that, there are a couple options. You could do a simple via style, top, middle, bottom, or full stack. And in this other section, you can select the hole size, you can select diameters. And in here, again, the template, you don't have to worry about it unless you need to change the template. I mean, the 64, this one is the default template that I had, so I keep it that way. And the drill pair is going to be from top to bottom. And we say, yeah, it's going to be top to bottom. Again, the same drill is a simple stack up drill, which is going to drill through your board. And you select a net, which in this case is ground, but you can via stitch different layers. Again, in this case, we want to ensure that our ground net has the absolutely minimum impedance. And that's why we like to via stitch our ground polygons. I'm force tenting on top and bottom layers. So when you tent it, you basically cover it up with solder mask. And here you can select the grid size. So it basically just means how far out, how far spread out do you want the vias to be. And in this case, I just put it 80 mils. One thing to note is the absolutely minimum number you can put in here is over 25 mil, because the diameter of your via is 25, so you cannot place them any closer than the diameter of the via. Obviously, try to say at least go with maybe like double the size of it, so like 50 or over, for easier manufacturability of your board. And then you just hit OK, and then Altium automatically connects or stitches all these ground polygons together using vias. So today we took the same circuit that we simulated last week in Altium, and we captured the schematic, we placed the components, all the passives around the IC, and we did the layout. It's very important to minimize all the high frequency loops that are formed in your buck switcher IC. So the first one is the input loop, where it's basically just from your input connector. Otherwise, it's the VN that goes through this connection. It's your VN and then back to ground. This has to be minimized. And again, as you can see here, we have it minimized already. It's pretty tight. And then another one is the switching. Again, it's one of the most important ones. The switching node has to be also very tight. That goes basically up from the switching node through the inductor and then back to the IC. And the last one that we call it a hot loop is the current that flows from the input. It goes through the input capacitors, goes through the same input pins, and then it goes through the switches. So basically it goes through the IC. In this case, they're both internal. So we have the high side and low side. It goes through the high side and the low side and back to ground. This also has to be minimized. We call this hot loop because this contains the largest magnitude of AC component, which basically means the higher frequency noise that can be present on your circuit, and you need to ensure that that particular loop is the smallest as it can possibly get. So this is it, guys. Thanks again all for watching. If you enjoyed this kind of content, please feel free to drop a like, leave a comment, subscribe if you haven't, and I'll catch you guys in the next video. Peace.